Okay, so welcome back, and we're going to use the concept of activity, ionic activity, in solving for the molar solubility of our precipitate. Okay, so remember last time that if your equilibrium constant is expressed in concentrations, this is the idealized version only. This is not the real version. The real version instead is in terms of the activities of substances. Okay, and we know that activity is equal to the concentration times the gamma, or the activity coefficient. Okay, so let's keep that in mind and let's proceed. So we have here silver iodide, and this will dissociate into silver ion and iodide ion. Okay, so I stable as usual. Okay, so since silver iodide is solid, we're not going to fill in any information in that column. Okay, so since this is also a diverse ion effect, so as you can see, potassium nitrate has nothing to do with silver ion and iodide ion in our ice table. That means there is no information about the concentration of silver ion initially and that of the iodide ion as well. So this is 0, this is 0. So if the product is 0, the change will be positive for the product. This is X and X. Okay. Then after that, we're going to write the equilibrium expression, KSP. Okay. Last time we corrected that we should write the equilibrium expression in terms of activities if stated. Okay, so we're going to do that. So that is equal to the activity of Ag plus times the activity of the iodide ion. Okay, so we can further expand this as the concentration of Ag plus times the gamma of Ag plus, the concentration of iodide ion times the gamma of iodide ion. Okay, so now we're going to look for this one and this one. Okay, so last time in solving for gamma, we can either use the Debye-Euclid equation or just look up into this table. Okay, provided that the ionic strength is present in the table. Okay, so let's try to see if the ionic strength is present on the table. So let's solve for solve for mu. Let's solve for ionic strength first. So solving for the ionic strength, this mu equals 1/2 the summation of the concentration of substance times the charge squared. Okay, so our diverse ion here is potassium nitrate. Okay, so we have 0.05 molar potassium nitrate. Okay, and potassium nitrate, this will dissociate into potassium plus and nitrate ions. So that means we also have 0.05 molar of K plus and 0.05 molar of nitrate ions. Okay, so that means the activity coefficient is equal to the concentration of K plus times the charge of the potassium, which is positive 1 squared, plus the concentration of nitrate ion times the charge squared. Okay, then we're going to substitute all the terms that we have. This is 0.05 molar times 1, and this is 0.05 molar times still 1, so this is equal to 0.05 molar. Okay, then since our ionic strength is 0.05 molar, let's check the table if it has a column for 0.05 molar ionic strength. Okay, so let's see. Okay, so here we have 0.05 ionic strength here. Okay, so we're going to use the table instead. Okay, so since we have that, we can easily look for the um, the ionic activity coefficient of Ag plus and that of the iodide ion. So let's just take a look at the table. So for Ag plus, we're going to look it up here. Okay, so this is Ag plus. So at 0.05, the activity coefficient is 0.80. For iodide ion, iodide. Okay, so this is the iodide ion. This is the activity coefficient, 0.805. Okay, so we have all the information that we need. Okay, so going back to KSP, KSP is equals to the concentration of Ag plus, let's zoom this, okay, times the gamma of Ag plus, the concentration of iodide ion times the gamma of iodide ion. Okay, then we're going to substitute all the terms that we know. Okay, so KSP, this is already given in the problem, and that is equal to 8.3 times 10 raised to negative 17 times 10 raised to negative 17. The concentration of Ag at equilibrium is X. The activity coefficient of silver is 0.80. The concentration of iodide is also X, okay? And the activity coefficient of iodide is 0.805. That means we're just going to solve for the value of X, okay? So we can simplify this as 8.3 times 10 raised to negative 17 equals, this is X squared times, what's 0.8 times 0.805, 0.644. Okay, so we're going to divide the equation by 0.644. So this is 8.3 times 10 raised to negative 17 divided by 0.644, and we're going to obtain the square root of that to solve for the molar solubility. So let me solve that. 8.3 times 10 raised to negative 17.644. Okay, so the molar solubility is equal to 1.135 or 14 times 10 raised to negative 8 molar. So this is the solubility of AgI in 0.05 molar potassium nitrate solution. Okay, so that's how we use activities when solving for equilibrium concentration.